Hello, this is a supplemental lecture for the electric fields unit of PHYS 1204. The main thing I'm going to do is get the E field due to a disk of charge, but there are also a few other things from various of the lectures in this unit that I want to clean up a little bit. We've already seen how to get the field due to a thin, uniformly charged ring of charge. We had a ring of radius capital R, and we're looking at a point P on the z-axis, which is the symmetry axis of the ring. And we broke it up into little pieces and integrated and found that this was the z component of the E field at point P, and by symmetry, the x and y components were 0. So now we're going to do the same thing for a disk, but we're going to use this expression that we already have for the ring to get the field due to a disk. So we have all the same geometry. We're looking at a point P, which is on the symmetry axis of the disk, and we're calling that the z-axis. And by symmetry, again, all the same symmetry holds, and so we know the x and y components will be 0, and we only care about the z component of this E field. And we're going to think, instead of breaking it up into tiny little bits like this, we're going to think of breaking our disk into thin rings. So in particular, the disk has a radius capital R, but we're going to be thinking of it as made out of a bunch of concentric thin rings, each with some radius R that we're allowing to vary, and each with some very small thickness, delta R. Also, this disk has some total charge Q. And one thing that's going to be useful to us then is that there is a surface charge density, so let's call it sigma as we usually do, which is going to be Q over the area of the disk. And so that is just Q over pi r squared. So each of these rings is going to have some charge on it, which we'll call delta Q, except it may be clear to you these rings aren't all the same size, right? The ones with small radius are smaller than the ones with large radius, and so we'd better specifically say that this is delta Qi for a ring of radius Ri. And one thing we're certainly going to be interested in is what that amount of charge is on a ring. So let's now start writing our E. So we know it's going to be approximately a sum over I of E fields due to rings. So I'm just going to write E due to the ith ring to schematically give the idea of what I'm doing. So I'm thinking of breaking this up into many, many rings, and I'm just summing over the E fields due to all of them. And so that means my Ez is approximately a sum over I, and we're going to go K. I'm just reading off the field due to a ring. So now the charge I'm going to call delta Qi on the ith ring, so delta Qi, and I have z, which is just the location of the point P still, all over, and now we have z squared plus, and this capital R here is no longer capital R, it has to be the radius of this ith ring, and all of that denominator is to the 3/2. So the main piece of work that we have to do is to figure out how much charge is on the ith ring. So let's look at that. Well, we can think of the ith ring as having some area. Should be equal to its length, or in other words, the circumference around it, times its thickness. Now, strictly speaking, that's not really true. When you have a circle with a hole in it, you would have to calculate the area of the outer circle and subtract the area of the inner circle. But if it's very thin, that's approximately just the circumference times the thickness of this strip. And so the area of the ith ring, so I'll call it AI, is the circumference, so 2 pi Ri, times its thickness, delta R. And so that means now, since we know we have a charge density, a surface charge density sigma, we can write delta Qi is sigma AI. And so now I can write my Ez is approximately a sum K, and I'm just going to copy all that up here. So I'm just going to take that and put it down where I can work with it a little more easily. And now I'm going to note what I'm going to have that's a constant. And I'm going to pull all the constants out. So the thing we're varying is r, right? And we'll need to leave the delta r in, because strategically in the integral, that's the thing that ends up telling us we're integrating with respect to r. So everything that doesn't involve an r is what comes out. So I've got 2 pi k sigma, and z is a constant. And all the rest of this I need to keep inside the sum. And so that means now when I convert it into an integral and it becomes precise, I just have to translate so that all of those things with I subscripts lose their I subscripts, and the delta becomes a d to tell us that this is our integral. And we have to integrate over r. We need to know the range. Well, we're going from the very middle, where r is 0, to the outer edge, where r is capital R. One thing that might mix you up is that z here is a constant, right? We're integrating with respect to r. This is actually a very easy integral, but I'm going to skip over that and just say, well, if you don't know how to do it, throw it into maple or Wolfram alpha, and it tells you that the antiderivative of this expression is this. And so we can write down our Ez. And I'm going to say, let's work with z greater than 0, right? If z is greater than 0, then the E field is up. If it's less than 0, it's down, and we'd have to think a little bit about some signs. The issue is the square root of this z squared and how to deal with that. As long as z is positive, we don't have to worry about it. And so a little bit of simplification. A nice thing to do is to take this z in, so this 1 over z and this z end up just giving you 1. And there's our final expression. It's probably not the least bit obvious that this has the right units, and in any case, after doing something this complicated, it's very good to check the units. So note that here we've got a length over a square root of a length squared, so a length over a length, and so that's unitless. Good, because this 1 is unitless. And so all of this in the brackets is unitless. We're left with this. Well, we have K, which is in Newton meters squared per Coulomb squared, times sigma, right? That is a charge per unit area, and so it's in Coulomb per meter squared, and so the meters squared are gone. This Coulomb takes out one of those Coulombs, and we get Newtons per Coulomb, which is correct units for an E field. As I said at the time, when I calculated this E field due to the thin rod, You may have felt like I was cheating by going and doing this integral in Maple. So I'll show you how to do this integral by hand, though I want to stress that throughout this course, you are not required to do integrals by hand. You can go ahead and plug them into some program or look them up on a table or whatever, because in particular, this integral is a sort which you may not have learned to do yet. If you're taking Math 1206, you certainly will learn how to do it, but you probably haven't yet. The key to doing this integral is to note that we have a constant squared plus our variable squared all to the 1/2. And when you have things like that sitting around in integrals, often a good way to carry out the integral is a method called trig substitution. So what you do is you build an imaginary triangle. Actually, in this case, this triangle is directly related to some of the geometry of the rod that we're talking about and the point where we're finding the field, but it doesn't actually matter. What we're doing is building an imaginary triangle. It's a right angle triangle, and so this side is here, and that's the key, right? That we've got x squared plus y squared square rooted, all cubed, and so this is giving us a relationship. And I'm going to define an angle theta right here. And the reason I've defined that is that now y over x is tan theta. So y is x tan theta. And I'm going to transform this into an integral in terms of theta instead of an integral in terms of y, which means I want to express this expression in terms of theta as well. And the easy expression is that x over our hypotenuse is cos theta. And so solving for this, that says root x squared plus y squared is x over cos theta, or in other words, x secant theta. This is where knowing your derivatives of your trig functions is useful, because we're going to need dy. And so dy is, well, x, and the derivative of tan is secant squared, and so then we have our d theta. So now I can rewrite this whole integral in terms of theta. Negative L2 is going to correspond to some value of theta. I'm going to work that out later. I'm just going to call it theta I and theta f. There's actually going to be a nice little trick. And I'm just going to substitute in. So dy is and square root of x squared plus y squared is x secant squared, and we've got all that cubed. And so that's now going to be a rather simple integral, because I have an x over x cubed, so that's a 1 over x squared, that's a constant and can just come out front. And then I have a secant squared over a secant cubed, which is 1 over secant, which is cos. And that's a pretty easy integral, right? The integral of cos is sine. Now, you might have to really scratch your head about how to do the final evaluation of this, because on the surface it looks really icky, right? We're saying, well, when we're at theta I, that's when y is negative L over 2, right? And so what's theta I? Well, you would say, well, y is negative L over 2, which equals x tan of theta I, right? And so theta I is apparently the inverse tangent of negative L over 2 over x. Well, that's pretty yucky, right, to put in here. But there's a way easier way, because you can just come back here and say, oh, look, sine theta is just y over root x squared plus y squared. And so when y is negative L over 2, sine theta is negative L over 2 over root x squared plus. And so this just ends up being. And if you check this against what I got in the earlier lecture, you'll see that it's exactly the same thing.